Okay. All right. Got all that set up now. So here is our format for exam number 3. And next to that, that is a picture of the formula sheet that is on the front of the test. So you're going to have all 3 Pythagorean identities. You may not even need to use them. Then we're going to have the double angle formulas. The half angle formulas, you probably won't need the half angle formulas unless you do a problem in a really weird way. Then we've got the sum and difference for formulas. You're only going to need one of them, but you don't know which one. Then over on the right, under the unit circle, we have the law of sines and law of cosines formulas, but they're not labeled. They're just there. And then underneath that, the bottom right, are the 4 polar equations. So the equations are kind of presented in the order you will use them on the test, more or less. I mean, we learned sum and difference before we learned double angle formulas, so technically the sum and difference should be up at the top, but they ended up at the bottom from the way I was having to do the typing. They ended up a little too close to the unit circle otherwise, so. But on the right, like law of sines, law of cosines, polar equations, that's question 3, question 4, question 5. So what questions do you guys have on this right here? Just what the setup's going to be for the exam. All right, so the exam review is it's on the long side. A lot of the questions are redundant to give you extra practice. A few of them are like a little too stupid looking for the test, but they're still like, you know, practice for the idea. So the first one I was going to pull was problem 4. So problems 1 and 2 are similar to problems 3 and 4. But the initial setup looks weirder. It is not going to look like problems 1 and 2. I'm just going to put it up side by side so you can kind of see the comparison between the way they look format-wise. So the format's going to be like problem 4. We're going to tell you sine of a triangle and where that angle is. We're going to tell you cosine of a triangle and where that angle is. And then we're going to ask for the sine of a plus b. And then we're also going to ask for like the sine of 2a or the sine of 2b or the cosine of 2a or the cosine of 2b. And it may not be sine of a plus b. It might be cosine a minus b. I don't remember what formula I put on the test. Just one of them. So for problems 1 and 2, it is the same question. They're just rolling everything that's spelled out in problem 4 into one compact statement. So this inverse cosine of 1/12, this is really telling you the cosine of alpha is 1/12. And then this inverse sine of 9/16, this is a placeholder for the sine of beta is 9/16. Now, because they did this with the inverse trig functions, though, alpha and beta are both in quadrant 1. So it's actually a little more straightforward because when you solve for the other trig function, everything will be positive. On the test, it's going to look more like problem 4 here, where we're actually going to have to consider the quadrant and whether stuff is negative. So I just wanted to give that as like when you're working those first 2 problems, it's just like these other 2, it's just the way they gave you the information is a little weird looking. All right, so sine of alpha plus beta. If we look at our formula sheet, this formula is sine alpha cosine beta plus cosine alpha sine beta. Easiest mistake to make here is to copy the wrong formula down, especially since you're having to flip the page over and back again. Yes, the exam review is still extra credit. Yes, I still haven't added in the extra credit for the other two exams yet. It will get added in there eventually, I promise. I have a whole column for it. I just haven't done the math. I will try to do that this weekend, actually. I have to go get my car worked on, so Sunday will be update all the grades day. Yes, if you get over 100 because of the extra credit from the practice problems, your grade is over 100 and it stays in the grade book that way. I haven't programmed them in yet, but yeah, if you got like a 94 and then like after test corrections and you got 100 on the exam review, then your score would be a 104 in the grade book. So that's like 4 extra points that can average in somewhere else and help you out. All right, so I know sine of alpha. I need to know cosine of alpha. So I need to draw a triangle. So sine alpha equals 1/8. Alpha's in quadrant 1. So I'm going to draw a quadrant 1 triangle. I put my vertical side back down to the x-axis. I label my alpha next to the origin. Opposite is 1, hypotenuse is 8. And I want to figure out my adjacent side, so I'm just going to call it x. So Pythagorean theorem, x squared plus 1 squared equals 8 squared. X squared plus 1 equals 64. X squared equals 63. So we do our square root of both sides. And we have our plus or minus question. But because we're in quadrant 1, x is going to be the positive square root of 63. The square root of 63 does reduce. I believe WebWorks should take it without the reduction, though. It's only Amplify that got like stupid about that. But we'll check when we get our answer here just to make sure. Certainly on the test, you do not have to reduce it. Like, how do I know it's in quadrant 1, or how do I remember which one's 1 versus 2? So they told us that alpha is between 0 and pi over 2. So 0 is directly right on the unit circle. Pi over 2 is directly up. So in between those is quadrant 1. So like our beta 1 over here, they tell us it's between pi and 3 pi over 2. So on the unit circle, pi is directly left and 3 pi over 2 is directly on the bottom. So in between those two puts the triangle down here in quadrant 3. Now, after you draw like the angle pointing into the quadrant, you finish the triangle by going from the end of the line back to the x-axis, and then that's where your right angle goes. And then the angle that we're talking about, they called it beta. That angle is always the angle whose end point is on the origin. So when that's beta, our opposite side is the vertical side, our adjacent side is the horizontal side. Cosine is adjacent over hypotenuse. That's caught another hippie. So our A side is -1. Our hypotenuse is 2. And we need to solve for the opposite side. So I'm just going to call that y. And the Pythagorean theorem, -1 squared plus y squared equals 2 squared. Now remember to use the parentheses here. -1 squared is +1. If you type it in your calculator without the parentheses, the calculator will tell you -1 because it's doing the exponent before the negative. Or it might tell you +1 if it's programmed like a little bit better. But either way, like you should know, a negative number squared is positive. Then on this next step, we -1 from both sides. So y squared equals the square root of 3. Sorry, y squared equals 3. I'm getting ahead of myself. And then we square root both sides, and we have the plus or minus there. Now, in our quadrant 3, we went left. That's why that side is negative. We're going down. So this side also needs to be negative. So I have the sine of alpha is 1/8. After I finished solving for x on the first triangle, I can say the cosine of alpha is square root of 63 over 8. Then my cosine of beta was -1/2. Then I solved for y, so now I can fill in that the sine of beta is the negative square root of 3 over 2. So beta, it turns out, is actually a unit circle angle, but doesn't matter. Because we really don't care what the angle is. We care what the cosine of that angle and the sine of that angle are. So now I've got all 4 pieces that need to go in the formula. So I'm going to write the formula down. Sine alpha cosine beta plus cosine alpha sine beta. So sine alpha is the same as 1/8. So in place of the entire sine alpha, I am writing 1/8. I am not writing 1/8 in place of alpha. Now our cosine beta, that was the other thing they gave us, that is -1/2 plus. Now our cosine alpha is the square root of 63 over 8. And the sine of beta was negative square root of 3 over 2. So once you have made the substitutions from the formula, done. You can actually type that answer on WebWork and WebWork will accept that. We didn't even have to break down the square root of 63. 63 is 9 times 7, so we could have written it as 3 square roots of 7, but you don't have to for WebWork. And you don't have to on the test. You don't even have to multiply the fractions on the test. That is good enough. And in fact, that is easier to grade. Now, if your brain just like needs to finish the work and wants to do the multiplication, like that's fine. But I will probably box this in your work and just put a check mark and ignore your work after that. Now, what if the question then followed up and said, bonus question or follow up? What's the sine of 2 alpha? So we already did all of our work for alpha, all of our work for beta. Sine of 2 alpha, we're only dealing with our alpha triangle. Now, our formula sheet says the sine of 2 theta is 2 sine theta cosine theta. So when we're trying to figure out the sine of 2 alpha, and we're using that formula, then sine 2 alpha is 2 sine alpha cosine alpha. I'm just trading out theta for alpha in my formula. And now I'm going to trade out what I know about alpha. I figured out the cosine of alpha was the square root of 63 over 8. And then if I scroll up, my sine of alpha was 1/8. And then my formula has the 2. Done. I just did sine 2 alpha. Just a quick little follow-up because I already had the work on the triangle done. So on the test, we just changed the format of the test. We used to give you a different triangle for the sine 2 alpha, and then you had to like do an extra triangle work, and it made a whole lot of extra work. And then the format we had for the first part confused people. So now the format looks like this. We give you the setup of 2 triangles. The first part asks you for one of the sum or differences, and then the second part is going to ask for one of the double angles. So if we scroll back, remember, that's what I said for question 1, sum and difference and double angle. It's going to be off of the same setup. Now, it probably won't be the quadrant 1 triangle, though. It'll be like at least one of those numbers is going to be negative. In fact, that's like the only downside on the test is we actually made both triangles ugly. So it reads better, but the setup is a tiny bit uglier from number perspective, but more straightforward. I don't know. We'll see how it goes. I have more confidence in this than the previous setup. So questions on the way that first problem is going to look on the test, the structure of it. Oh, the sine 2 alpha? No, you can just leave it like that. 2 times fraction times fraction. I don't think web work even makes you multiply it out on these. Like web work for most of these is programmed to, as long as it's equivalent to the decimal answer, it's happy. And it's kind of like that from here, like all through Cal 1 and Cal 2. Most of the time in Cal 1, they don't actually want you to calculate the decimal. Like if you just type in the horrible math thing that you were going to put on the calculator, WebWork will actually take that as the answer. It's only on some of our pre-cal questions that it's still programmed. Like basically it's programmed from a high school perspective because high schools all have to take standardized tests. And on standardized tests, you have to simplify the answer to match it because it's multiple choice. All right, let's see. So problems 1 through 4 are sum and difference. Problems 5, 6, and 7 are double angle, but they each give you their own like setup. Unfortunately, they're all in quadrant 1. On the test, it will be a different quadrant. Now then, problem 8 is a stupid looking equation. Problem 9 is a slightly nicer looking equation because the only fraction is inside the trig function. So I'm going to grab problem 9 because problem 8 is too stupid looking for the test. It's still good practice, but it's just the initial numbers were really dumb. Like instead of -4, it's the problem that has the like square root of 3 over 64 or some shit. Just unnecessarily stupid looking front numbers. All right, so question 2 on the test is solving 2 trig equations. Our first trig equation is going to look like this. They're both going to have the qualification that you're only solving for numbers between 0 and 2 pi. So to start solving for x, we've got to start clearing out all the stuff around the x. So the 1/2 is the closest thing. Then next closest is the sign of that. Then next closest is the -4 being multiplied. And then that -1 is the furthest out from the x. So the -1 is the first thing that we're going to get rid of. And we're going to get rid of that by adding 1 to both sides. So I have -4 sine of 1/2 x equals -2. And then I divide by the -4. I have the sine of 1/2 x equals positive 1/2. This is the step where we go to the unit circle. So where is the sign 1/2 on the unit circle? So let me go yoink a picture of the unit circle real quick. All right, so sine, the y value is 1/2. There's one, and there's the other. So our angles are pi over 6 and 5 pi over 6. Now it's really tempting at this point to be like, there, my answer is done. But these are half of x equal these unit circle numbers. And also, whenever we pull the number from the unit circle, this is where the 2 pi k goes. Now, if you forget the 2 pi k on this one, it'll actually still work out okay, but technically you should have it. Now, to get rid of the 1/2 with the x, what do we do? So how is that 1/2 attached to the x? Is being added, subtracted, multiplied, or divided? So the 1/2 is being multiplied to the x. So I can divide by what I'm multiplying by. I can divide by 1/2. Dividing by a fraction is the same as multiplying by the reciprocal. So I can also multiply by 2. And whatever I choose to do on one side, I choose to do on the other. So now x is by itself, and 2 times pi over 6 becomes pi over 3, plus 2 times 2 pi k becomes 4 pi k. And then we also have x equals 2 times 5 pi over 6, the 2 and the 6 reduce, so it's 5 pi over 3 plus 4 pi k. So the plus 4 pi k means if I pick a k value besides 0, my numbers are going to get 4 pi larger or 4 pi smaller, which would make them negative. So my extra k values will not produce extra solutions. In fact, sometimes this step where you multiply by 2, it can even make the bigger angle too big. Now here, because we were dealing with sine, it actually works out. So both of these are still between 0 and 2 pi. But if it was a slightly different formula or a different trig function, it's actually possible to have only one or no solutions. Now, we don't do a no solution on the test, like that's just too weird. So here, our final solution is pi over 3 and 5 pi over 3. That's what we'd type in for web work. So notice if I didn't write the 2 pi k, I wouldn't have the 4 pi k, but I would still have those same two numbers. So if you forget the 2 pi k, you can still solve it and I'll still count it just fine. So right now I have half of x, right? I want to get rid of that half of x. So get rid of the half. One of the ways I could write that is write divide by a half, but then I'm dividing by a fraction. Dividing by 1/2 is the same as multiplying by the reciprocal of 1/2. So the flip of it would be 2 over 1. So I was just writing times 2 because writing divided by 1/2 gets a little ugly looking. But if you did that on the calculator, like pi over 6 divided by, and you put the 1/2 as a fraction or in parentheses, it'll spit out pi over 3 or 1/3 for you. So if you want to write it all as divide by 1/2, that'll still work. So technically, this is the step when we would plug in the k numbers. So k equals 0 gives us these two numbers. K equals 1 is going to be too big. K equals -1 is going to be too small, which means it'll be negative results. So we only have to plug them in when they're going to give us solutions between 0 and 2 pi. So yes, we don't care about the 4 pi k because it's going to make the extra solutions bigger than 2 pi or smaller than 0. And we're doing like all of those qualifications, the too big and too small is because of that 0 less than or equal to x less than 2 pi qualification that they snuck in at the beginning. So if you're not sure, like plug in k equals 1 in the smaller like base formula, the pi over 3 plus 4 pi. Well, if I'm adding 4 pi, which is bigger than 2 pi, and I'm adding to it, that result's going to be bigger than 4 pi, way bigger than 2 pi. If I subtract 4 pi's from pi over 3, I'm going to get something negative. So you can plug in the numbers to test it, but if the answer is too big or too small, like you don't have to write it down. So generally, you know by actually plugging the numbers in and trying it out. But there's also a like when you solve enough of these, like you get used to when it matters and when it doesn't. Generally, the k values only matter when we're doing like trig function of like 2x or 3x. Like when the thing inside that's being multiplied to x is bigger than 1. So since this one was a half x, that's why the k values ended up not mattering, because we were actually giving us like answers that were more spaced out instead of answers that were more clustered together. So when we do the 2x and we divide by 2, it turns the 2 pi k into pi k. Then we're adding less, so we get more numbers. Now, I will say the problem I skipped, number 8, was a 2x problem. But I, for random reasons, went with number 9. Yes, randomly. We all remember what randomly means, right? Somebody say it out loud because I can't. Right. All right. Now, when we look at 10 and 11, we've got factoring. So I'm going to go with problem 10 because it's the numbers are smaller. Like problem 11, they basically multiplied everything by 3, I think, or 6. So it's like bigger for no reason. The problem on the test that matches this is actually it has multiple ways you can solve it. But this one, like, we're stuck with factoring. So we have 2 cosine squared plus a cosine t is equal to 1. So the first thing I'm going to do is I'm going to subtract 1 so that everything is equal to 0. So 2 cosine squared t plus cosine t minus 1 equals 0. Now, we have a quadratic written in terms of cosine of t. If looking at the cosines is too much for you, we can trade out the cosine t's for u for ugly. So it'd be 2u squared plus u minus 1. We can also just factor it in terms of cosine t. Or if you're not comfortable factoring, you can use the quadratic formula. The end quadratic formula result would be for u equals a number or u equals another number. And then our u is cosine t. So any of those methods, like whichever way you are most comfortable getting from a quadratic to getting to the results of a quadratic, that is what you do on this next step. I'm going to factor it, but I'm going to do my u substitution. So we have 2u squared plus u minus 1 equals 0. And there's really not a lot of choices here. 2u and u, 1 and 1. And then one of these has to be positive and one has to be negative. I want the outer one to be positive and the inner one to be negative. So the outer pair, 2u times u is positive, and then 1u times u is negative. So that way they add to a positive u. So now that I have it factored, I set each factor equal to 0. 2u minus 1 equals 0. So add 1, divide by 2. We have u equals a half. And u plus 1 equals 0 gives us u equals negative 1. So I did a lot of work, but those are u solutions. If you did the quadratic formula, these are the two numbers you'd get out of the, negative b plus or minus. Like after you do the plus 1 and the minus 1, you'll get these two numbers. But now we got to bring our substitution back. Cosine of t is 1/2. Cosine of t is negative 1. Now we go to the unit circle. So where is cosine of t 1/2? So that's short x closer to the y. So this is pi over 3. Technically plus 2 pi k. And then the other place cosine is positive is over in quadrant 4. So we're going to go all the way to 5 pi over 3. And then cosine is -1. So to remember when cosine is one of the extreme values, I think of the graph of cosine. So cosine is at an angle of 0, cosine is 1. Then pi over 2 is 0. An angle of pi gives me the -1. So this is when t equals pi plus 2 pi k. So those are my three solutions for t. That's my final answer. Now, I don't remember, WebWork might make you type them in order. Maybe. I don't remember if it does that. I don't care if you write them in order on the test. Like you can just box all three of the individual answers. That's fine with me. Or 4 answers, 2 answers, however many you end up with. Sure. So we take our 2u squared plus u minus 1 equals 0. So our quadratic formula is, do you want me to write the quadratic formula down? All right, so b is 1, so we have -1 plus or minus the square root of 1 squared minus 4 times 2 times -1, all over 2 times 2. So that's -1 plus or minus, this becomes 1 minus -8. So 1 plus 8 is 9. So we have -1 plus or minus the square root of 9 all over 4. So -1 plus or minus 3 all over 4. So -1 plus 3 all over 4 is 2 over 4, which is the 1/2. And then -1 minus 3 all over 4, -4 over 4 is -1. So the same solutions we got, and then we would write cosine of t equals 1/2, cosine of t equals -1. Now you don't have to show me like all the individual steps there, but that was me just like showing all my work, writing it out a lot. In fact, you can even like, you could do like all of the number crunching quadratic stuff like as scratch work off to the side, as long as it makes sense to you. And then you end up with just those two numbers. Like I'm fine with that. Like how you go from the quadratic to the u equals or cosine equals step, whichever way you want to do it. And it doesn't have to be like pretty math for me to grade as long as it made sense to you. I've graded a lot of work though. I can probably still follow it. All right, so that took care of the first two questions on the test. The sum and difference in double angle, and then the two trig equations. Our next one is the law of sines. Now, it is not a double triangle law of sines case, but it is the angle side-side setup. So I'm going to go find the angle side-side triangle, which I think is problem 15. Nope. Where is it? Nope. Oh, there it is. It's problem 13. So this is the same as the double triangle problem from the 5.1 homework, the one that everyone hates because it's so buggy. This question is the same buggy question, but it's because the calculations we do in this problem are the calculations you will have to do on the test. You're going to have to use law of sines to find an angle, and then use law of sines to find a side. You just won't have to do the second triangle part. Now this setup is a two triangle setup, but I'm just going to do the first triangle. And I'm going to redraw the triangle because I hate theirs. On the test, we're not going to draw the triangle for you, so you can draw it in whichever way you want. So I'm just going to go with my big flat side, long diagonal, short diagonal. They gave me angle beta, so that's what I'm going to call that left angle on the triangle. And they told me that is 37 degrees. That means the side opposite beta has to be side B. And side B is the ridiculous 6.36492. Then the other side they gave me was side C. And I make side C my other diagonal side. That makes the angle opposite C angle gamma. We could also call that angle C if you want. But our law of sines formula from the formula sheet has sine alpha over A equals sine beta over B equals sine gamma over C. I think that's what we put. Yeah, we wrote it with the alpha, beta, gamma. Now we're going to use just the second two parts of the law of sines. And we're solving for gamma. So I'm actually going to start with the sine of gamma, just because I like to have my unknown on the top left, divided by side C is 10. And then this equals sine of beta. So the sine of 37 degrees divided by ugly decimal 6.36492. To start getting gamma by itself, I'm going to multiply by 10. So the sine of gamma is, leave some space, 10 sine 37 over 6.36492. And now to get gamma by itself, we use inverse sine. So I'm applying inverse sine to both sides of the equation, but notationally, we write that inverse function in front of what we're applying it to. So it's kind of like a square root. You don't write the square root after the number, you write it in front of the number. And now that is a calculation to type into the calculator. Make sure you're in degree mode. Especially if you were using your calculator to figure out what those angles were on the equations, the trig equations. Those angles were in radians, but now we need our angles in degrees. So my calculator's still in degrees, I'm good. So inverse sine function, 10, regular sine 37. And remember, the calculator opens a parenthesis when you type sine, so you have to close it, divided by the 6.36492. And then we close the big parentheses. And gamma is, because of the way this problem is programmed, 71.000038. On the test, the angle will be a stupid number. It will not be close to a pretty number. I did not pick the numbers to try to come out with a pretty angle. So just round it to like 2 or 3 decimal places and you're good. If you just want to carry the whole decimal through in your calculations, that's also fine. I'll figure it out based on what you write on your paper. But for the way this web work question is programmed, gamma is now just 71. So now that I know gamma, now I can backtrack and figure out alpha. because I also know beta. So alpha has to be 180 minus beta and minus gamma. So 180 minus 37 and minus 71 is 72. All right, so I figured out gamma, I figured out alpha. Now I just need to figure out side A. So I'm going to come back up to my law of sines formula. I'm going to start it out with A over sine of alpha. And this is going to equal, and it doesn't matter which pair of sides and angles you pick here. So you can go with the B's or the C's. I just habitually go back to the pair they gave me. So I'm going to do B over sine beta. So A over the sine of 72 equals 6.36492 over the sine of 37. And we multiply both sides by the sine of 72. And that gives us our calculation for A. 6.36492 times the sine of 72, close parentheses, divided by the sine of 37, close parentheses. A is 10.0585, 7, blah, blah, blah. All right, so alpha was 72, gamma was 71, and we just got A to be 10.05857. And for once, it actually liked them in the top triangle. What a shock. I was really expecting it to be like, I hate your answers, and we'd have to move them. So for the test, done. All you will have to do is just this set of calculations for the law of sines. There is not a second triangle on the test. But for finishing this for web work, I'm not going to finish it, but the gamma prime angle is always 180 minus gamma when gamma is that first angle you found. So what is that, 109? So then you can calculate a different alpha prime from that and then use the same setup to calculate side A prime. Now let's see. All right, I'm just going to yoink 15. 15 and 16 are very similar and very similar to the setup on the test. And I do give you a drawing on the test. But I don't label them A, B, and gamma. I just put the numbers in those positions. So you would have to come up with the letters. So on the test, it'll have 230 feet, 405 feet, and then the angle here they said was 62 degrees. So the law of cosines formula we get from the list is the c² version. So it is written c² equals a² plus b². So it looks kind of like our Pythagorean theorem, but then with an extra crazy minus 2ab cosine gamma. So the only angle in this formula is gamma. Go for it. So in the book, there's actually 3 versions of this formula. There's one that starts with a², one that starts with b², and then this last one starts with c². I only wrote this one version on the test. So that's why I didn't label the diagram. But they're all equivalent. They're just like trading the positions for the a's, b's, and c's. So the angle label here is gamma, and the only angle we know is 62 degrees. So 62 degrees has to be gamma for us to use this formula. That means the side opposite gamma is side C. And that is the side that they're asking us to find the length of. So that means the other 2 sides are A and B, and it doesn't matter which one you call A and which one you call B. So I usually just go A on the left and B on the right. But if you swap it, the formula still works the same. All right, so now we're just filling in the numbers. So A is a huge 230 plus B is 405. So I have 230 squared plus 405 squared minus 2 times 230 times 405 times the cosine of 62. Now remember, you want to type that whole thing in one line on your calculator. Don't break it up. That is where people make the mistake on this one. I know it's a lot to type. I know it's going to like run too far on the screen, but this is what works best. So I typed 230 to the second plus 405 to the second minus 2 times 230 times 405 times the cosine of 62. And I get a stupid number. 129,462.44 blah, blah, blah. So we know the lake is not 129,000 feet across. Because we need to square root. So I raise it to the 0.5 power, and now I get a number that's more in line with the other numbers. 359.80890, blah, blah, blah. The directions did say round to at least 4 decimal places. So it's almost 360 feet. I do give you rounding directions on the test. But if you do a different number, like not the end of the world. Now, if I built a bridge across the lake there, and then I asked, if you were going to walk all 3 sides of this, how much would you walk? How would you figure it out? So if we're going to walk the edges of this triangle, like what do I need to know for how far I walk? all the side lengths. Yep. And I've got the first two they gave me, and I just found the third one. So if I wanted to know what's the distance all the way around, just add all the sides for no particular reason. But I say that because some people get so hyper focused on the way we solved all the triangles that asking what to me is like a common sense question, their brain will just like break and they're like, I don't know. So if your brain totally breaks on that question, go to the second question and write add all the sides. You know two of the sides, so write number plus answer from A. And that will get you 5 points. I just had somebody do that on my calculus test. They didn't know how to find the slope, but for the last part of the question, they were like, here is the equation of the line. Here is where the slope answer would go. Here's where the other numbers are. And I was like, yes, that is what you would do. Even though you didn't have the number from your calculus work, you still get credit for this last part. So always write something down. All right, now our last part is polar dealing with the polar coordinates. So I'm going to grab problem 20. So there's more than problem 20 in there. Like they have the, are these polar points the same or not? Because we used to have part of a question that kind of did that, but we took that part off. But it's still good practice. So this one says, find the polar coordinate with theta between negative pi over 2 and positive pi over 2 for the following Cartesian coordinates. And they tell us the x, y, and then they're asking for r theta. So our polar equations, let me go find those real quick. So there is our four polar equations. That's what they look like on the front of the test. So I got the x equal and the y equals formula, and then I got the x squared plus y squared equals r squared, and the tangent theta equals y over x. So I know x and y. I need to figure out r and theta. So I know x is -8. And I know y is +5. So which formula am I going to use to figure out r? Yep, the top right. Because I know x and y, that's why I highlighted them, and I don't know r, and that formula has the two things I know and the one thing that I was asking for, the r. So x squared plus y squared equals r squared. And now we fill in -8 for x and +5 for y. So -8 squared plus 5 squared equals r squared. So that is 64 plus 25, which is 89. Cool. So r squared equals 89. And then we square root. And we have to remember the plus or minus in front. And right now, I'm just going to leave it as plus or minus the square root of 89 because I don't know which of those I want yet. All right, now we're going to use the other formula that had y and x in it to find theta. So the tangent of theta is y over x. So tangent of theta equals, leave some space. My y value is 5 over my x value is -8. And to get theta by itself, I'm going to use inverse tangent. Now, because they told us theta has to be between -pi/2 and +pi/2, they gave us pi numbers. We have to put our calculator in radians mode. And it's not going to be a pretty number. I mean, none of the numbers in radians are pretty. So the inverse tangent of 5 divided by -8. And see, I forgot to change my mode, so it spit out -32. And I'm like, that's not a radian number. There we go. So -0.5585. Because the y is +5. Because that was our ordered pair. It was -8 comma +5. I mean, like, 5 divided by -8 is -5/8. If you type in inverse tangent and -5/8, it'll give you the same answer. Fair. All right, so now I've got these numbers. I need to figure out my theta number, -0.55. That is smaller than -pi/2. -pi/2 is -1.57. So this is the angle I'm stuck with. I can't change my angle. If I added 3.14 to this, it would be bigger than pi/2. If I added 2 pi, it would be way too big. If I subtracted pi or subtracted 2 pi, it'd be way too negative. So this is the only angle I can use that fits the description. So I have to figure out, do I want the positive radius or the negative radius? And this is where plotting the point comes in. So my point is -8, +5. That is in quadrant 2. My angle right now, my theta, is in quadrant 4. So if I use a positive radius, the positive radius will put my point in quadrant 4. I need my point to be in quadrant 2, so I have to use the negative radius. So it'll equal r equals the -√89. So our r theta point will be -√89, comma, -0.5585. Now there is no pretty number. There is no pretty pi number that -0.5585 equals. It's not some like magical 7 pi over 22 or something. No, that is just the ugly decimal. Now on the test, I do need to see your work to produce the theta number. So this way, if you type in, like if the calculator was in the wrong mode or you fumbled it a little, I can see the calculation and see that you had the formula correct. So our angle is -0.5585, so that's in quadrant 4, right? But our point, our XY point, -8.5, if we plot that point, that's left and up. So the point is in quadrant 2. So if I kept my theta the same and used a positive radius, the positive radius would be down in quadrant 4. So like A, not the answer, but this location here is the positive square root with the negative angle. This question didn't let us change the angle. We had to use what came out of the calculator because that's the restrictions on inverse tangent. So I had to choose between my positive and my negative radius. If they'd let me change the angle, I could take my negative 0.55 and add pi to it, and then that would also be an equivalent polar angle to my answer, but it's just not in the restrictions the problem provided with me with. So we had to use the negative radius to move backwards into quadrant 2 from our direction. Did that help, or is it still a little fuzzy? So remember, when we're plotting polar points, we turn to the direction. So the negative 0.55 means we're turning clockwise. So we're moving from our 0 direction and we're turning kind of backwards to look into quadrant 4. Then our radius tells us which way we're going to move and how much. So if my radius is like positive 2, I turn, so I'm like facing the wall, and then I'd scoot forward like 2 feet. But if my radius is negative 3, I'm still facing the same direction, but I'm going to back scoot 3 feet. So the angle tells me which way I point my chair. The radius tells me how much I move and which way I move. Yeah, that is one of the weird things about polar is it really does help to be in a swivel chair, as silly as it sounds. Yes. Like if you typed in it's 32 degrees and change, if you typed it in with the 32, it'd be like, nope, it's only programmed to accept the negative 0.55. And we're stuck with that because the qualification had theta between negative pi over 2 and positive pi over 2. So that's what's forcing us to use radians, is the way they wrote that qualification. Now, certainly like the degrees would probably communicate the idea better, but sometimes when you're using these formulas in an applied setting, like radians is the way the function is programmed in the computer. And converting to degrees requires extra calculation steps that if you just thought about the problem in radians instead, you wouldn't have to write those steps in. So that's like the only reason we really do radians, is just because that's how most like the behind the scenes computers, that's what they're running. All right, one more. 21. The good news is it's short. So we have the Cartesian equation x squared plus y squared equals negative 4y. And we're being asked to come up with a formula in polar form. So that means only in terms of r and theta. Sorry. Now, the good news is we've got our same 4 polar formulas. So 2 ways to go about this problem. I have formulas for x and y. And I can just shove them in there. Poof, now the formula is only in terms of r and theta, and I am done. That is what they asked for. They asked for it in polar form. Like on the test, polar form, done, r and theta. On web work, though, web work asks that we have to get it R equals. So we're going to be a little more creative in our substitutions. But notice here, x squared plus y squared. Why is that so familiar? Yep, it's straight up equals r squared. So there is my first substitution. I have the mixed equation r squared equals negative 4y. Now I know y is the same as r sine theta, so I'm going to write that in. So I have r squared equals negative 4 r sine theta. Now, for the purposes of web work, we're going to do something that in any other circumstance we would not do. We're going to divide both sides by r. So we can only do this because of the weirdness of polar. But normally dividing by a variable is an absolute no-no because you're dividing a solution out. But here the r's would cancel and we're left with negative 4 sine theta. So r equals negative 4 sine theta. So negative 4 sine theta is what WebWork wants you to type in. But r squared equals negative 4 r sine theta is a solution. Or there's an even sillier looking equation where I'm just going to substitute in for x and y. So x is r cosine theta. And y is r sine theta. That is a polar equation. It's a real stupid looking polar equation, but there's no x's and y's. It's all r's and thetas. I will take that answer on the test as well. WebWork won't take that, but I will. So you can simplify it down to r equals negative 4 sine theta if you want on the test, but you don't have to. All you have to do is convert it to polar form. Done. So, hour and 15 minutes, we covered everything on the test, which is more than my other two classes have for the test, but that was also me explaining, answering questions, clarifying questions, weird extra points, like ideas. So this is doable, but you just got to be on task, focused, ready to go. So for this is the second half of the last problem. Is this what we did right here? But the part before it, that's where you need radians. But for your law of sines and law of cosines, that's where you want it in degrees mode.